Everyone, it's a pleasure to have you all with us here today, so please be welcome. Just some quick information here on the beginning. So cameras and microphones, I would like to ask you to keep it closed. For the questions later, please write it on the chat where you have the opportunity to talk and discuss with you all later. And then also to be in conformity with our policies, I would like to start informing you that this event will be recorded. So if you do not feel comfortable with this and you want me to disconnect, no problem, feel free for it. So my name is Rafael Regatieri. I am part of the SAMP Brazil technical team. SAMP is an international organization created targeting to share and spread the knowledge of engineering process and advanced materials. We have our HQ in the US and we have 40 chapters spread around the world connected in this mission. Today we will have our first event dedicated to the composites recycling. The event will have 1 hour with 2 presentations and then later time for us to discuss the questions. So again, feel free to write the questions here on the Google Meet chat. We are very happy to host Vanessa Amaral de Oliveira and Professor James Waterhouse for our event today. Vanessa is graduated in Material Engineering at the University Federal de Santa Catarina. Then she later obtained her PhD in Material Science and Engineering from Grenoble Institute of Technology in France back in 2016. And then she has been working at Extractive ever since. She's in charge of operations of Extractive Chemical Products, which is the chemical branch of Extractive, and she's the project leader of the recycling carbon fiber. Professor James is graduated in Mechanical and Aerospace Engineering, Master in Composite Materials and Aluminum Laser Manufacturing, with PhD in Aircraft Renewable Fuel. Nowadays, James spreads and shares his time between being professor at the Aerospace Department at the University of São Paulo, his company, Aeroalco, which is a producer of small aircraft, and also being consultant with large experience in engineering and it's also a very well-known entrepreneur here in Brazil, being one of the founders of Ares Energy. So now we would like to start our presentations. We will start with the presentation of Professor James. So Professor, please go ahead. Thank you and enjoy the webinar, everyone.
Thank you, Rafael, and good evening, everyone. I'll try within 20 minutes making an overview of the composite recycling problem. And nowadays, composite recycling is actually a problem, not a solution yet. So we're gonna see a possible solutions. So Rafael has already presented me, so I'm gonna go quick with the presentation. So I'm gonna try to show you the main source of plastic, reinforced plastic fiber, mainly fiber reinforced plastic for recycling. So the main concentrate source of composite materials to be recycled came from wind energy, especially the blades and the fairings. But what about all the composite materials used in our society, especially on new aircrafts? Well, the aircrafts are pretty new, so they are not need to be recycled yet. And all the other composite uses came from several thousands of products all spread around, and they're not concentrated. So our society, most of our society does not have a way to segregate the composite materials to be recycled. So if you have few kilos of composites, that's not viable commercially to be recycled. So most of our composite components goes to the landfill and goes into the domestic garbage or industrial garbage and goes to the landfill at this moment. And that's quite a shame, but anyway, there's a great future for that. For the wind generators, the things are quite different just because the wind generator's lifespan is less than 20 years. We expected 20 years of life, but most of the wind generator does not reach the actual 20 years lifespan, mainly because of early blade failures, etc. But we can consider 20 years lifespan. And the wind energy is getting older and older, so the wind farms need to be replaced in favor of new machines and modern machines and bigger machines, what we call repowering. So most of the old wind generators are among 1 megawatt, 1.5, maybe 2 megawatts. So they're quite small machines. So they contain approximately 25 tons of composite on the blades and fairings altogether. The actual machines easily go to 60 tons and maybe more. The onshore machines are around 60 tons now of composites. The offshore machine can be several times that, but they're just starting to be commissioned. So that will be a 20-year from now problem. Most of the fiber to be recycled and composite to be recycled came from this old wind generators. And I would like to give you a quite wide overview before getting to the composite recycling problem, just because the wind generator is all in one piece. And it contains a steel tower that weighs around 150, maybe 350 tons for those quite old machines. And some of the wind generators use a high-strength concrete, just because a bit cheaper and a bit easier, because they are manufactured the precast concretes are precasted on site, so they have a little bit less logistic cost, but they use a huge amount of concrete, up to 1,500 tons of high-strength concrete. And the nacelle itself will weigh between 50 and 150 tons. That most of it will be cast iron, but you have a copper, you have rare earth, and you have a reinforced plastic for fairings, etc. on the nacelle. And the foundation itself, there's another thing to be considered, weight between 500 and 1,500 tons. So what that means? That means after some time, we need to decommission the whole thing. We just cannot leave the wind generator after 20 years just as it is, just because it imposes a high risk for the society, because we will eventually fall down and create a huge risk for human life or animal lives all around. So you need to disassemble it. And for disassemble it, you need a huge crane capable of 90 meters height or maybe more, and with a huge capacity. A crane like that, if using for the whole wind farm decommission, so you can share the fixed cost of the crane between all the machines that need to be decommissioned. That means around $10,000 up to $30,000 if you are using as a whole farm. If you need to decommission isolatedly, then there will be a huge cost, just because a crane like that needs around 10 days, using like 15 trucks and 10 people just to be assembled. It's an enormous cost. So just to get the wind generator down, it's a labor-intensive activity, and also a respectable risk activity, just because it weighs a lot and you have a lot of risks for human life all around. So there's not cheap to put the whole thing down. And also, you need all the logistics around for the workers and cranes and trucks, everything. And that means a huge cost. Who's gonna pay for this cost? Most of the countries not even thought about the commission, just because the wind energy was something such new and everybody was very enthusiastic in early beginning. And everybody forgot to put responsibility for the commission. So for the investors, there's quite a respectable cost, and everybody trying to quit from this cost. So there's gonna be a normal legal problem for everyone, for governments, for investors, for everyone, until decide who's gonna pay for the whole thing. For the new contracts, most of the countries are requesting to the investors a warranty for decommission the whole thing. But just for the new contracts, old contracts, most of the machines are not covered on that. So there will be problems around. And how can we recover part of this cost of decommissioning the whole machine? Well, we can try to recycle the materials the wind generator contains. So we can sell the steel for like around 15 cents of dollars per kilo. That means between 200 up to $50,000 for the tower itself, plus between 7 and 20,000 for the nacelle itself. That means we have around 27 up to $70,000 of recovered money. That not even close to pay the whole expenses for the commission, the whole thing. Just because we have the concrete. If we does not have a concrete tower, we sure have a concrete foundation. For the tower itself, that have a bit lower cost, then we're gonna have a huge problem, just because a tower is composed by high-strength concrete. And try to break down high-strength concrete into small pieces that requests a quite powerful hydraulic jaw fragmenter that's not very cheap to operate. So the whole thing costs around $40 per ton just to fragment it, plus the logistic to bring this material for someone to be used. Most of this recycled concrete could be used in roads and things like that. So it has its use, but the problem is most of the wind generators are located very far from the potential buyers or user for this type of material. So the logistic cost could be also extremely expensive. So it may be worth just to fragment it and leave it all around, minimizing the environmental impact. But the foundation is another huge problem. The foundation itself has a lower grade concrete, but it's buried on the ground, so it will cost you a fortune to remove it from the ground. You request a hydraulic hammer and a huge excavator, plus a concrete crusher and a truck. So there's almost twice the price for the tower for each ton. And especially if you want to repower in the site, any environmental authority will request you to just to remove the whole thing and start it again. One should ask, if can I just leave the concrete there? Well, all depends on environmental impact and authority for that. And to reuse the foundation is not a good idea, just because the foundation does have fatigue also, not only the towers and the blades. So this is gonna be very, very expensive, and the steel cell or copper cell won't cover the cost. And what's gonna happen with the composite materials, mainly the blade materials? So this could be a game changer for the whole thing. Now, what they are just doing with it is just putting to a shredder to fragment it into small pieces, just because composite materials is very light. So it's light. If I do not fragment it into small pieces, the logistic cost will be much more expensive than actual cost. That's still expensive. So you need to improve the density. And the default use right now is just a landfill that will cost you around $20 per ton. Depends in each country, each region does have a landfill cost, different landfill costs. But this is not the way to do things for the future generation, just to bury the problem. And also, most of the landfills are hundreds and hundreds of kilometers away from the blades. So the logistics costs, again, gonna be very expensive. So in Europe, whereas the problem is happening right now, just because Europe was the first part of the world that's starting with the wind generators, they are using a lot of composite to fuel cement furnaces. But the problem is the old blades, especially the old blades, contains a high amount of glass fiber that's basically silicon oxide and some other oxides. So the ashes that came from these processes are dominant. So that's like 80% ashes and 20% of hydrocarbons that could be burned and generate energy. So this turns quite expensive. So maybe the cement factories, instead purchase the material, will charge you to use these materials and neutralize this material. And you're gonna waste the whole fiber content just because you're gonna melt it. The cement furnace are high temp furnaces. That's a good news. The bad news is most of the blades and almost all the blades contains a PVC foam inside, and PVC contains chlorine, and chlorine with the temperature and carbon just form dioxins and furanes. That's extremely toxic for human life, extremely toxic. So a small amount of PVC gonna generate a massive amount of dioxin and furanes at high temps and uncontrolled burning way. So this is another huge problem for this type of material. So there's not a good news. Most of the new blades are trying to remove the PVC in favor of other synthetic foams that could be recycled. That won't be the case because it will be extremely difficult to recycle the foam itself, but at least does not form hazard chemicals at high temps. So that's a good news. So the other process will be pyrolysis. Just put the parts of the blades into a vacuum chamber and heat up around 500 degrees. You cannot heat up above 500 degrees just because we're starting to form a lot of hazard materials also, and we'll start to form dioxins and furanes again and other things. So you have to keep the temperature quite low, and the process take quite a long time to be vaporized, to gasify the whole plastic content. But after a couple of hours, you're gonna vaporize or gasify most of the hydrocarbon contents, almost all of it, and you're gonna remain with the mineral charging and the fiber itself. So you can reuse the fiber if you use a pyrolysis process. That's the good news. And also, when you gasify the hydrocarbons, you can condensate it into some oils, heavy, light oils. So you're gonna have a lot of things to be condensated plus the gas. So you have energy, hydrocarbons energy that you can use as fuel. But if you have a large amount, you can use it as a chemical raw material, but it needs a really high amount of this type of material to justify it. And won't be the case for decommission of the wind blades, just because wind blades are in the middle of nowhere, far from everything. So probably one of the best ways to do is just take a pyrolysis unit that could be mounted in skids to the wind farm, and you can run the whole process into the wind farm itself and make it quite a cost-effective process and bring the liquid hydrocarbons to some place else to be burned, and also the fibers. And the fibers could be reused, not for the noble use, but could be reused for tiles, insulation, and other materials. There's other possibility to use a fiberglass scrap from the wind blade industry as the old blades, as a filler for composite industry. A lot of composite components just use fillers like tubing and other things. But the problem is the filler amount we use is very small compared to the amount of fiber that we're gonna have within a few years. So, and also the logistic cost and the fragmenting cost will be quite expensive. So that could be a good thing to recycle the scraps on the wind blade factory when the blade is new, just because they are using some fillers direct on the process and the scraps are there. Most of the wind blade industry, I do think all of them are not using yet. They just sending to the landfill, something like that, unfortunately. And then we have other process I want to talk about, just because Vanessa will focus on those process. And this is more or less what I have prepared for you, just because I have only 20 minutes. Thank you very much for your time. And now I think, Vanessa, it's your turn.
Perfect, Professor. Thank you very much. We'll have some questions for you later. Now we will pass the turn to Vanessa. So Vanessa, please.
Yes, I'm trying to open the presentation. Just give me a second. Okay. Are you seeing my screen?
Yes.
Okay, perfect. So thank you very much for the invitation. I'm going to talk about FIRE. There is a new recycling technology for the recycling, indeed, of carbon fiber reinforced plastics. And I'm going to start actually talking about Extrative, because Extrative is a French SME that is dedicated to the circular economy. We are mainly specialized in the production of secondary raw materials, and we decided to specialize on this production mainly because we can decrease the risk of supply of this material in Europe. We can give a material that's going to have a low carbon footprint, which is especially interesting for local production and local sourcing, and also the affordability of this second life material, because we have a low price and wastes that can be sourced easily. So Extrative operates today in 3 different locations. We have a total of 4 employees, and in 2019 we generated a revenue of around 3 million euros. As I said, our products are diverse and are used in diverse companies as well, such as foundry, ceramics, and plastics. We have one operation that is dedicated only for the recycle of ceramics, which includes alumina, silicon carbide, and other type of ceramics material. We have an R&D team that has today 10 people that only works in the custom-made recycling process. And it was in this R&D team that the FIRE technology was born 5 years ago. And we have also a unit that is specialized in the recycling of specialty materials, which includes indeed the recycled carbon fibers, but also lithium salts such as lithium carbonate. So to get into the subject of today's webinar, I'm going to start talking a little bit of life cycle analysis. Today, especially in Europe, there is a lot of legislation and regulations that is limiting the CO2 that can be emitted by cars and mainly all transportations. So for example, if we have a car that is 30% lighter, we have a reduction of 50 tons of carbon per ton of carbon fiber in 10 years. If you consider aircraft, if they are 20% lighter, you're going to have a reduction of 1,400 tons of carbon per ton of carbon fiber in 10 years. So it's a huge decrease on the emissions, and it's very interesting to light the transports. However, the production of the carbon fibers is a very, very intensive, energy-intensive material that can emit up to 8 tons of carbon per ton of carbon fiber produced, which is huge. However, this production is increasing because the market is in need of this carbon fiber in order to go for lightweight. And that's all this demand for carbon fibers and all this lightweight that we are looking for does show that there's an opportunity finally for the second life carbon fibers, especially for automotive, sport and leisure, and no structural parts in the aeronautic industry. So just to resume, we have today a high consumption of composite material based in carbon fibers. So we have a lot of end-of-life pieces and a lot of production scraps being generated today. We need to find a viable recycling solutions in order to answer the need of the market for lower cost carbon fibers, and mainly a carbon fiber that has a lower carbon footprint. So that's how FIRE was born. Actually, today the main recycling process for this kind of material is pyrolysis, as Professor James just presented. However, pyrolysis, it does still have a quite high carbon footprint, especially because of the high temperatures that they use, and they can damage a little bit the fibers as well. So we have limited the capacity of using this carbon fiber, especially in high value materials afterwards. So the FIRE process was born in order to have a very high quality material without damaging the carbon fibers that can be used in high value applications. So mainly we're going to collect composite scraps. We're going to put in a large reactor. We're going to put a mix of chemical materials that's going to degrade the matrix of this composite material. We're then going to recover the carbon fibers from one side, recover the oligomers from another side. So the oligomers are today going to be valorized in chemical companies as a byproduct, and the carbon fibers can then only be sent directly to compounders if you want to normal valorization of this carbon fiber, where for sure there is a market of this recycled carbon fiber, or we can go for different ways of post-processing in order to go for high value added applications. So I'm just going to show a little video where we can understand a little bit more about the process. So this is the reactor that I told you about. So in this reactor, we actually have a basket. We are going to introduce the composite material inside this basket that's going to then be introduced inside the reactor. We're then going to add the mix of chemicals. We actually have a solvent and a catalyst. The solvent is going to, we're going to heat it up to 180 degrees. And actually at this temperature, the chemicals are in vapor phase. So here we have a pressure that is around 10, 11 bars, which is the auto-generated pressure of these chemicals. That's going to actually degrade the matrix. So after the solvolysis process, we're going to recover the solvent, the catalyst, and the oligomers of the degraded resin. And in the basket, we're going to have these carbon fibers that are ready for the washing steps to be valorized. The chemicals are then going to be distillated. So it's just a simple process of distillation where we can recover the solvent and the catalyst for a new use. so they don't need to be disposed. And through this distillation step, we can recover the oligomers that are then going to be sold as a byproduct for the chemical industries. So this process has the advantage of not damaging the fiber, so we can recover really high quality material. We have the full recyclability of the composite material, which means we can recover the carbon fibers, but the oligomers as well. And it's a process quite versatile. I'm going to show you later what kind of metrics can degrade it. We have a lower carbon footprint as we work at lower temperatures and the chemicals are reused, and it's also a process that has a lower cost. So continue, as the process itself is quite static, we can recover, if the material is still woven, we can recover the still woven material after the recycling, which can be interesting, especially for applications in the sport and leisure industries. Or we can recover long fibers that can then be processing into yarns for higher value applications. So here are some characterizations. Here are images took using a scanning electron microscope, where we can see that we have almost no trace of residual resin within the fibers, and we can see that there is no damage in the fiber itself. Here are some mechanical characterization where you use it. In this first part are single fiber characterizations. We have a very similar tensile strength when we compare virgin carbon fibers with recycled carbon fibers. We have a loss that is less than 2%. We have seen no influence on the strain at break when we compare both fibers. And we put as well these virgin carbon fibers and recycled carbon fiber inside composite material, and we have done some mechanical properties tests where we see that we don't see actually any difference, significant difference between the recycled fibers and the virgin fibers once they are inside the composite. So here's the versatility of the process. Actually, what happens is that the chemicals are going to cleave the carbon-nitrogen or carbon-oxygen bonds in the matrix. So the process works very well. It's very compatible with epoxy resins, cyanide ester, polyamide, PPA, PEI, vinyl ester, PEEK, and other types of resin, thermoplastic and thermoset resins. Using PEEK and PPS, we have to change a little bit the conditions, but we can still have good resin degradations. However, because of how the process cleave the bonds, it's not compatible at all with PP, PE, and PMMA. However, we do have a large part of the market, especially regarding the epoxy resins, that can be well degraded in our process. And what happens with the oligomers? So here we can see a textbook example of how we can valorize these oligomers as a byproduct. Here is a case of polyamide 6. In order to avoid any contamination of the sizing of the carbon fibers, we use it in this case only pellets of pure polyamide. We put it in the solvolysis, and then we recover this white powder. We then analyze this white powder using different techniques. And what we show is that it's actually mainly a precursor of caprolactam. And caprolactam is actually a monomer of the polyamide 6. So this caprolactam can be directly sold to the chemical industries to redo polyamide. So this technology was actually created five years ago in 2016 using an European program that's called EU START. We then scale up this process up to 1 kilogram per day in order to optimize the system and especially the solvent recycling. We have since then acquired different kinds of national and European funding in order to scale up the technology. So today we are here in our pilot phase where we can treat around 100 kilograms of composite material per day. And today we are already starting to buy all the equipment for the big demonstrator that's going to be treating 1,000 kilograms of composite material per day and should be installed in 2022. So here is our 800-liter pilot. We are mainly use it in order to treat representative samples of composite material, as we can put around 100 kilogram, which is quite representative. We want to work doing different kinds of realignment of this recycled carbon fiber and test different kinds of post-processing in order to have a product that is more homogeneous to sell in the market. And as well, we want to provide this recycled carbon fiber to end users in order to validate our material before we start the commercialization. So there are different opportunities in this recycling. Actually, we only think about, okay, so the recycled carbon fibers can be valorized as for compounding, but not only. So here is the case where we use, we are going to recycle a hydrogen tank. For those that don't know, the hydrogen tank is mainly made of carbon fibers. This one is with epoxy resin. And we have put this in our 800-liter reactor. We have put the chemicals. We wait for the time. And the video is not working. Well, it's a shame.
Maybe
actually,
because of the pointer, Vanessa. Could be that you are the pointer.
Okay. So I'll try to remove it. Okay. So yes, in this case, we can unspool actually the carbon fiber from the tank, and we can recover almost a semi-continuous fiber, because in this case we have 4 kilometers of carbon fibers. So yeah, it's a very high quality carbon fiber that we can have different uses once it's recovered. So there's a lot of market opportunity for this second life carbon fiber. Our goal is to work in semi-finished products in order to provide more homogeneous quality, which is required especially for the automotive industry. We can imagine doing unidirectional tapes or sheets where we can maximize the mechanical properties. Of course, we can always go for no woven mat, where it's easily to use and to be employed by the end users. And we are also working in our collaborative projects in producing a kind of yarn that can be used as well for the end users. These carbon fibers, recycled carbon fibers, can be used for pieces in the automotive industry. So here is a piece that is done for one of our partners, that's Meyer company. We have as well done these prototypes that are used in non-structural pieces for the aeronautic industry. We can imagine something similar as well for the nautic industry. And of course, in the sport and leisure would be the most simple and also a niche market where we can easily use these recycled carbon fibers in skis, in bike frames, rackets, and many other endless applications. So now, today, we are focused in our Helicarrier project. It's a project that is funded by the EIT Raw Materials in Europe. It's a project that is ongoing and is going to end by December 2022. And the goal of this big project is actually to prove the competitiveness of this soft-voice recycling process. The goal is to increase the level of maturity to TRL 8. And we're going to assess all the properties of recycled carbon fiber in new composite material. We're going to confirm that we can indeed valorize the oligomers and the recycling of the solvent. We want to establish a complete life cycle analysis and cost in order to show the competitiveness of the process among all the other recycling processes that we have today. And finally, to reach the market of recycled carbon fibers. So mainly to finish my presentation, we have shown that the fire technology has been shown to be a promising technology for the recycling of composite material. We have well validated at laboratory scale, scale-up phase, and now in pilot scale as well. We have the possibility to sell losing fibers, but we can sell as well steel woven material, and even semi-continuous fibers when we are recycling, for example, hydrogen tanks, as I just showed, which can definitely open new market alternatives for recycled carbon fiber. The beginning of this process industrialization will start by 2022, and the first unit is going to be able to recycle around 300 tons of composite material per year. So this is just a small timeline to show where we were in 2016 with really the beginning. We put the first patent in 2018. The scale-up experiments starting as well in 2018. We have secured the funding of the EAT raw materials of 4 million euros in 2019. In 2020, we're beginning this pilot scale experiments, and finally now we are preparing everything to start the industrialization in 2022. Thank you very much, and I'm open to questions.
Thank you, Vanessa. Thank you, Professor James. I think we can jump to the questions. I would maybe start for the ones that we have here on the chat. The first one that we have is for Professor James. So Sergio is asking you, Professor, related to, can you please highlight the proportion of the wind farm market that is adequately addressing these recycling issues? And if you see as well, is there any regulation on the topic in any country of the world? Okay. If not, is there any groups dedicated to working on construction of this type of standard for this regulation on recycling?
As the Europeans are the ones that really concerned about the environmental, they are the pioneers into this legislation and also addressing the problem. So they funding a lot of research and projects all around recycling and solving this problem. So in Europe, they does have a quite mature laws for it. So you cannot install a wind farm without the warranties to decommission and recycle, or at least have some neutralizing of the raw material. But in other parts of the world, and in US, the problem now is starting to happen. In Brazil, the new auctions, you have to, that's part of the new contract for the wind energy auctions. But for the old wind farm, nobody really addressed the problem. So this will be case by case. Each country and their legal system will try to address case by case.
Yes, this last comment, I think, came into the direction of the Leticia question here, because she mentions that we have already some blades that having been used in Brazil for at least 20 years. So do you know how these types of discards is doing? Do you have any information on what we have been doing locally?
Actually, it's going to the landfill. There's very, very few wind generators older than 20 years in Brazil. And there are quite small units, so they are just scrapping and sent to the landfills at the moment and recycling the steel. That's what's happening. And our wind energy really starts around 2008, 2009. That's what the ramp up was serious. Before that, it's just very limited units installed around.
And do you see, maybe, as you said, we'll be maybe 6 years from now to really start to face the problem, really on the decommissioning? Do you know, based on this best practice that you mentioned earlier with the European legislation, if we have some type of committee here in Brazil that is working, dedicated to it, or is it something that's not really yet, started yet?
Not yet. So nobody really worried about this or doing something towards the problem. So they are just trying to send to the landfill as much as they can, as we do with our domestic waste. So the recycling industry in Brazil is almost nil. So unfortunately, we have a huge amount of garbage to be recycled, as we're gonna have a huge amount of wind generator, as also on a very near future some boats, because the boats, there's another huge source of composite materials. So the boat industry lasts more than 20 years just because it doesn't have a fatigue problem, etc. But eventually they're going to start to be recycled also, or to be scrapped and sent to the landfill. So there's no serious committee right now to address this problem in Brazil.
Okay. Thank you very much, Professor. Maybe moving now for some questions to Vanessa, also one from Sergio that we have here. So he started, of course, exalting the good presentation that was done, and how would the second life of these carbon fibers perform on the structural parts, and would that be ever a route, and if there's a standard that helps the market to qualify these recyclable materials for this, let's say, more structural parts use?
Yeah, the main problem is mainly on the certifications indeed. So we know for the aeronautic industry, every time that we need to certify a new material, it's several years to do it. So that's why for the aeronautic or defense industry, I don't think for the short time, I would say in the next 10 years, will be possible to use a recycled carbon fiber for more structural parts. However, the automotive industry, for example, their certifications are much less exigent, let's put it this way. In this case, I think that it would be possible, in this case, to use for structural parts. However, no, I am not aware of any other new standard that can help to qualify this kind of material to the market, which is a shame, and I hope more industries that are interested in using these recycled carbon fibers can maybe unite to give new standards for these different industries.
Very good, thank you. And the rest of his question was related to what's the cost impact of such process in maybe dollars per kg per residual?
It's complicated talking about costs right now because we are not commercializing the fibers yet. I can maybe give a range between $3 and $6 per kilogram. But it's really a range and can be quite optimized, especially depending of what's the coming product, what's the percentage of carbon fiber that we can find in the product that we are receiving. And also, if we want to focus on recover the final woven material or only short fibers, this changes completely the cost of the process.
Thank you, Vanessa. The other question is also one that I would make as well. So if the firework firework process also works for different type of fibers, like fiberglass or aramid, it was the example that Sergio bring to us here.
Yes, indeed, I haven't said in the presentation, but the process works very well in glass fibers as well. We had degraded a lot of wine blades, indeed, and we can recover the glass fibers like really, really neat, and we don't have any problem with this. However, using aramid fibers is more complicated because they can be damaged in the process. So we tried once and haven't focalized since. However, we really decided to focus more in the carbon fiber, mainly because of economic reasons. Because today is much more complicated to find a use of recycled glass fibers than carbon fibers. So mainly for economical reasons, we start to focus in carbon fibers.
Very good. We have another one from Leticia, and she said, Vanessa, when do you believe that compost recycling becomes commonplace?
Well, with recycling, actually, legislations helps a lot. So we are lucky that here in Europe, legislations are quite strong regarding recycling. And in Germany, actually, landfilling of composite material is not possible anymore. So this really push into recycling alternatives, and that's why the recycling of composite material is really growing in Germany mainly, but we know that's going to propagate into the other European countries soon as well. So yeah, definitely here in Europe, we are already starting talking about the recycling of composite, at least as a more commonplace, at least in the near future. I know this is quite a long road still for Brazil or maybe even United States.
Very good, very good. Thank you very much, Vanessa. We hope that this came also common sense for us in Americas as soon as possible.
Yeah.
So we have a question from Rafael for both of you guys. And then he asks, with the reverse logistics becoming reality in Brazil, are the current manufacturers of the wind blades able to get back to a type of deconstruction or decommissioning or reuse of any part? So do you see something happening? Maybe you, Vanessa, also in Europe to comment, and you, Professor James, here in Brazil, something like that?
Vanessa, you can answer first.
Yeah, I think it's complicated. That depends because especially the carbon fibers or even the glass fibers in wire blades are mainly used for the structural part. So it joins the first question of Sergio of what's the certification of the use of this recycled material in kind of structural pieces. But if it's validated in using in more structural pieces, yes, I think it's totally possible to do it. I know that for the aeronautic aircrafts, it's already possible to recycle some pieces and then the manufacturers reuse it, but in non-structural pieces. So why not do it the same thing in wide blades?
Okay, I do think for the blade itself, the recycled fiber will be very difficult to be used as the structural requirement is very tough and is becoming tougher and tougher. One of the problems with composite materials, the spread of mechanical properties. So everybody's trying to address this problem. That means better raw materials, etc. But remember that wind generator does have a lot of fairings that are secondary structures that may use recycled fiber easily. So for the blade itself, no, but the fairings, yes. For the glass fiber, I don't think will be cost effective, as the glass fiber cost per kilo is very low, and the logistic imposed by all those processes are very expensive. And when you remove the whole thing chemically or through the thermal process, you remove all the sizing of the glass fiber that absolutely needs to be reused for structural components, even for secondary structural components. So I think the secondary use for glass fiber will be very low-grade materials. Unless you can advance the process, but that's a matter of cost. That's very different for carbon fiber. For carbon fiber, it's much more expensive material, and the sizing problem is not huge as the glass fiber. So probably you can reuse for secondary fairings into the wind industry.
Very good. Thank you, guys. In fact, I have a question for both of you. That I would like us to discuss as well. It's what do you think that's the most important properties for recyclability? Do you think it's really more the material itself, or the process and the way that the material was done has influence on it? And then we also heard during the Professor James presentation about the PVC, that this, when we try to do recycling, it's very bad for health and safety. So how do you think that this is being taken in consideration for new designs? and how will be the future in your opinion? So a two-step questions for you guys, please.
Professor James, if you're okay, I start and then you continue.
Okay, I may start. So as the recycling laws advanced in Europe and turns this into a necessity or obligation, so you must do it. Designers are going to start to think with this in mind. So the cost of the recycling will be on the generator, and to use PVC would just be expensive compared to other foam material as example. So we can avoid the PVC just because we're gonna cost a lot to recycle and gonna create problems. So this is gonna address more and more the wind industry, not only the blade itself, but the tower. So like the concrete's quite cheap to be used, but extremely expensive at the end of the life. So this is going to impact the design decision and the raw material purchase decision. So there's more and more going to happen, and this is going to stimulate by the law, the regulation, and then the people going to start to realize we not much driven by regulation, but by the common sense on the future.
But from my vision of things, at least here in Europe, much of the end users are interested in a new material, a second life material, mainly because of the lower carbon footprint. They want to give this image that they are using a lower carbon footprint material that has a greener image for their products. Also, of course, the price. You're not going to pay for a recycled product more than you can have material, so price is also very, very important. And also the profits. So there are some standard of profits that you have to meet. So yeah, this is probably going to be the three main pillars that the end users are looking to in order to be able to use this second life material.
Very good. Thank you both. Maybe the last question of our session today, it's from Diego. He's asking to Vanessa, how many times it's possible to recycle the same part using the fire technology and still maintain a good property?
Well, that depends on what's going to be the use of this material afterwards. Only for the damage that we can put in the process itself, we recycled up to 5 times without observing any loss. But indeed, during this recycling process, we haven't used the material. So this is going to be a more long-term study to see really how many cycles we can really do in real life material in real use. But we know that the solve process itself is not damaging the material.
This is really nice, and for sure can help to understand how this life cycle will be very important, maybe even for the science itself. It's good. I like it very much, the question. Then Sergio is reminding us one of the things that we always like to ask to our guests when we make events in SAMP, it's, in your vision, what do you think that SAMP can do to help the market to incorporate the decommissioning strategy as part of the product design, and what would be the actions that you think that we can take, maybe together, with the government maybe, or with research institutes? We would like to hear from you. What do you think, how SAMP can play this role in the composites market?
I just think that first of all is just spreading information is a really good starting point, and then stimulating a committee and things like that to discuss the problem in direction to create a decent regulation, because the regulation must be something that we can comply with, and we shall advance it as a technology advances also. So to give this fine tuning to the regulators, because sometimes regulator tends to be too tough and then creates another problem, especially like in Brazil. If you put a too expensive or too difficult regulation, everybody skips and gonna fragment everything and bury it in any place around without without anyone seeing. So this illegal problem that we can see all around Brazil and other third countries. They just bury the problem, or not even bury. They just throw the used parts all around, and nobody's liable for that. So I think to have a decent level with the acknowledgement and cost compatible with the country, that SAMPIC can really can help on this.
I joined completely the answer that gave Professor James. It was a very complete one. So yes, definitely helping this dissemination, especially to companies and politicians.
Very good. So guys, if you have no other questions, I would like to thank you all again for joining. Special thanks to our guests, Vanessa and James. It was really nice to have you with us today. And inform to you all that we'll have this webinar available later on our YouTube channel. Thank you very much. Take care, you all, and we keep in touch.
Thank you very much, Rafael, and thank you, Vanessa.
Yes, thank you very much, Professor James. Thank you very much, Rafael, and all the team of SAMP. It was very pleased to be here.
Thank you. Bye-bye.
Bye.